Good morning, good afternoon, good evening. My name is Sandra González Gallardo, and I am the Deputy Editor of ChemCatChem and the European Journal of Inorganic Chemistry. It is my pleasure to welcome you today to our virtual symposium, Main Group Catalysis, which is brought to you by Chemistry Europe. Today, we have three excellent talks by Professor Robert Gilliard, Dr. Josep Cornella, and Professor Eva Hevia. Our moderator will be Professor Rebecca Melen, who obtained her PhD degree in 2012 at the University of Cambridge. Following postdoctoral studies at the University of Toronto and the University of Heidelberg, she took up a position at Cardiff University in 2014, where she is now a reader in inorganic chemistry. Her research interests lie in the main group chemistry area and the applications of main group Lewis acids in synthesis and catalysis. And therefore, she is one of the guest editors of our special collection on main group catalysis, together with Professors Georg Harder and Shigeyoshi Inoue. Rebecca, thank you for being with us today. The screen is yours.
Thank you very much, Sandra, for the kind introduction. And I look forward to everybody's contribution to this special issue on main group catalysis. So as Sandra said earlier, we have an excellent lineup of speakers this afternoon, and I welcome everybody to this virtual event on main group catalysis. So yes, we have three speakers this afternoon, and I would say that these speakers are really helping to drive forwards the field of main group catalysis, as we will see later on in these talks. And if you have any questions for the speakers, please write them in the question box, and then we will be able to go through these at the end of the talks. So this brings me on to our first speaker this afternoon. This is Professor Robert Gilliard, who obtained his bachelor's degree from Clemson University. He then undertook his PhD degree at the University of Georgia, working in the laboratory of Professor Greg Robinson. He then undertook postdoctoral studies at ETH Zurich and Case Western Reserve University. Following this, he joined the faculty at the University of Virginia as assistant professor in 2017, where he currently is. And also this year, he is a visiting professor at MIT. And so the floor is yours, Robert. Looking forward to hearing your talk on redox flexibility in the main group.
Okay, I'm trying to remember how to share the slide now. Okay, now, thank you. So, okay, thank you, everyone. Thank you to ChemCatChem and the European Journal of Inorganic Chemistry for organizing, as well as Rebecca and the rest of the guest editorial team. I appreciate the opportunity to speak today. I'm going to be talking to you about redox flexibility in the main group from a structure and bonding perspective, and really introduce a little bit about how we see main group redox chemistry and the potential impact on catalysis. So I'm going to talk a little bit about some of the differences between the D block of the periodic table and the main group elements, both the S and the P block. In my research group, we like to study main group elements for several reasons. One is the very unique bonding and reactivity that you can obtain, sometimes very different from what you would observe with transition metals. And then more recently, you see a lot of people studying transition metal-like chemistry of main group elements, meaning that main group elements can facilitate a lot of the chemistry previously reserved for transition metals. We also like main group elements because they're pretty earth abundant. When you look at some of the most active metals, most of them are transition metals that we're very accustomed to, things like palladium, rhodium, ruthenium, iridium, very key elements in catalysis, also in CH bond activation and so on and so forth. But when you start looking at some of the more abundant elements, you will find a lot of main group elements, things like bismuth, elements we use in my group, boron, beryllium, even some magnesium. You can see that they're very earth abundant. Some of them are some of the most abundant elements we have access to. Bismuth and other elements have the additional property of being non-toxic. And so that's why we're really interested in the bonding and catalytic properties of these elements, because typically speaking, their earth abundance also correlates with cost. And when you think about the future, we think that this is going to have a major impact moving forward. So one of the differences between transition metal and main group chemistry is that one of the most prolific, I would say, catalytic systems is based on palladium zero. We've probably all used them at some point. And of course, Suzuki, Negishi, and Heck won the Nobel Prize in 2010 for carbon-carbon coupling chemistry. So it's pretty standard to be able to isolate these zero-valent palladium complexes, and a lot of zero-valent transition metal compounds exist. And you can easily do an oxidative addition to get to, for example, the palladium-2 species, and then you can reductively eliminate to get back to your catalyst. And so low-valent and high-valent transition metal compounds are well established, and that's why there's so much catalysis known based on those types of elements. And when you change the story to main group, it immediately gets more complicated. So it's pretty challenging to even isolate zero-valent main group compounds. And even if you're lucky enough to be able to do that, the oxidative addition to a higher valent species can also be a challenging task. And so even if you're able to do that, getting back to the starting catalyst is really challenging. This happens, but by a select number of main group elements, which I think one of the reasons or things we will have to do moving forward is to be able to understand the fundamental chemistry of how we access these low valent species and how we perform these fundamental reactions of oxidative addition and reductive elimination, because they're just not as common with the main group elements. And so this is talked about in detail by Phil Power, who covered in this Nature article the perceptions of main group element chemistry versus transition metals, of course, highlighting the fact that with main group elements, you're dealing with S and P orbitals, which were historically thought to be far apart energetically, usually colorless compounds, and generally do not react with small molecules. Of course, we know that that is not always the case anymore, and a lot of people are calling this or referring to this as contemporary main group chemistry. The bonding models that we use have evolved. Of course, you can use ligands to change the disposition of the orbitals, so the orbitals are not always far apart. And that leads to a lot of colorful main group compounds, and many of them do react with small molecules. The challenge going forward will be, how do you make those types of systems catalytic? Because again, there aren't many examples where that's the case. And so one of the places where we started in my group is looking at the bonding characteristics of alkaline earth metals. And we started working with beryllium and magnesium. And even between those two elements, there's already a lot of variability. Beryllium likes to form covalent bonds, while magnesium forms a lot of ionic bonds. Beryllium is really charge dense. And so there's incredible variability in the bonding as you go down the group from beryllium to barium. Again, with beryllium being really charge dense and giving properties that are unlike the rest of the elements in group 2. And so with that in mind, we took a look at the literature at the time, and of course, one of the most prolific ligand systems in group 2 chemistry is this beta diketamine ligand, or these formerly anionic ligands. Some refer to them as NAC-NAC. So you can take these types of ligand systems and bind them to alkaline earth metals. Of course, in this case, one electron is used in bonding with the ligand, giving you one reactive group. And if you reduce them, you can get to these dimetallic systems. And of course, the first example of such a compound like that was by Cameron Jones and Stash back in 2007. This is not the NAC-NAC ligand, but they also prepared that one as well. There have been other examples of these low valent group 2 complexes. Of course, the really recent result, beautiful chemistry by Sword Harder that recently appeared. The last example I'm showing here of this calcium 1 mediated N2 activation is not a subvalent molecule itself, but that was formed due to a intermediate that was calcium 1. And so again, that's what we've all believed for some time, that these low valent species, if you can form them, you can do, for example, N2 activation or transition metal-like chemistry that would normally not be the case for higher valent species. And so, of course, you can take these, not only are the low valent species relevant to catalysis, you can also form cations as well. So you can do a halide abstraction, for example, to get to naked cations or cations with weak interactions with various anions. And so folks like the Harder group and the Hill group have prepared these magnesium cations and showed them to interact with various organic substrates as well. And so these are, in my mind, catalytically relevant species. And so we started asking ourselves early on, what can we do that's a bit different? And we changed the ligand system. Instead of using these formerly anionic ligands, we use the neutral ligand systems. And so I mentioned before that in the top example that one electron is used in bonding here, that's not the case when you have a neutral ligand binding to an alkaline earth metal. And so you can have two groups to do various reactions with on these, using these neutral states. And of course, if you do reduction chemistry, you can get to these ligand stabilized alkaline earth metal systems where they're in the formal oxidation state of 0. And of course, one of the first examples of that was by the Braunschweig lab back in 2016. But you can also do halide abstraction and start to form cations. And of course, in this case, the cation still has a reactive group there because it's not, again, the electron is not used in bonding. So that's just some of the strategies that we've been using. And to do that chemistry in my group, we've mostly used carbon donor ligands, both carbenes and carbones. We use the N-heterocyclic carbenes, cyclic alkyl amino carbenes. Those are pretty well-known carbenes at this point in time. Of course, they're 2 electron donor systems. The carbone system, or the carbyl dicarbene, is pretty different in that it doesn't have an empty p orbital. You have this filled p orbital, and so unlike carbenes, at least formally, it can serve as a 4 electron donor system. And so we took advantage of all of these ligand systems in our chemistry. We spent a bit of time at the beginning trying to get to reduce magnesium systems. And we first tried to do that using this large carbene, this 2,6-diisopropyl substituted carbene. We reacted it with magnesium halides. If you do the reaction in THF, you get to this tetracoordinate species. And this THF is pretty labile. It can come on and off. Even in solution, we can see evidence for the formation of these dimers. If you add THF back, of course, you get back to the tetracoordinate species. But this is not a scenario that you want when you're trying to do reduced chemistry because it's difficult to purify. We actually had not an easy time there. So one of the strategies that we use is instead of having these larger bulky ligands, we simply use isopropyl. And if you do that, you can get 2 groups or 2 carbenes on the magnesium center. It forces this to be a terminal reagent. You can get all these different starting materials in pure form, including this methyl bromide, this kind of carbene stabilized granular. There was one before this, a monomeric system published by the Mulvey group back in 2010, I believe. And so we used them to do all different types of reduction chemistry. I should say that was pretty challenging, but we were actually able to form the relevant cations using those strategies. Both with 2 carbenes, we can make the dication. We can also make the monocation using these strategies. And so we also determined that you can take a carbene and 2 carbenes reacted with magnesium bromide. You get to the dicarbene complex. You can actually add in a 3rd carbene as long as the carbene is small enough. It actually weakens the magnesium bromide bond, and you can form the cation this way. So it's kind of a base initiated approach to magnesium cations. And so we're in the process of following up on these different compounds as well. I should mention that we have all of the crystal structures. And one of the questions that always comes up is, how does this reactivity compare to the anionic ligand systems? Because these are base stabilized. And I'm not going to talk about that in detail because it's still being worked out, but I'll just say that in these particular carbene complexes, because they're base stabilized, these carbenes can come off in solution. And so what we see is that when a carbene comes off, the magnesium center becomes more Lewis acidic, and then it can react with small molecules. And a lot of times the carbene will come back on in kind of a self-assembly type approach. So they do react with small molecules, it's just a different method. And so one of the other things we were studying in the group at the time was how do we get to these low valent beryllium compounds? And we had a lot of challenges reducing beryllium-2, for example, to beryllium-1. And so we switched ligand systems. We started with the CDC beryllium dichloride complex, and we wanted to use the di-HMDS complex as a starting material, but it turned out that we could only prepare this heteroleptic species where there's one chloride and one HMDS group. And so it turns out that if you do a reaction with the potassium HMDS to try to get a second equivalent of HMDS attached to beryllium, and you actually form this beryllium cycle. And we fished this out. It was in pretty low yield at the time, 10% or so, but we were able to recognize there's a formal loss of a chloride. So the question became, if we reduce it, do we get to the same compound? And it turns out that we do, and in much higher yields. This is one of the first examples of CDC beryllium complex that could be structurally characterized. And that had us thinking about potential beryllium-1 intermediates. It was pretty much a consensus in the review process that it likely was proceeding through this type of a mechanism. So we were already interested in beryllium-1, as I mentioned, trying to reduce from beryllium-2 to beryllium-1. And so it ended up with, we couldn't get there via that route. And so we ended up taking the formerly beryllium-0 complex, a different derivative, reacting with TEMPO, and we were able to get to this beryllium radical cation with this unusual beryllium anion. The compound on the screen was very challenging. We were able to crystallize it out, but if we tried to do anything else to it, it would essentially decompose very rapidly under most circumstances. And it was the case that the only scenario that we could find that would work would be sodium barf in ether, which would allow us to make the barf analog. And once we did that, we can actually characterize that complex. And when you start to think about redox cycle, if you view this as beryllium-1, we go to 0. The question is, can we get back to the starting material? And we can, at least stoichiometrically. So you start to see something that looks like a cycle. So this is the type of chemistry that we're going to be following up on. We hope to do this with magnesium as well. Of course, a different strategy is going to be necessary. We've structurally characterized these as well. I'm not going to talk about the structures in detail because of time today. We've also been studying the oxidation chemistry of these types of species, and we reacted the beryllium-0 compound with TMS azide to get to a complex with an unusually short beryllium-nitrogen bond of 1.464. And we discussed this as a double bond between beryllium and nitrogen. We're actually not the first one to mention that. The 1997 paper by Phil Power actually comments on potential multiple bonding between beryllium and nitrogen, and they reported a bond distance in this terphenyl complex of 1.519. And again, this bond distance of 1.46 is pretty short. It's shorter than the computed bond distance for beryllium-nitrogen double bond. It's also shorter than the sum of the covalent radii. And this paper was pretty timely considering the very recent report by Magnus's group on this first S-block metal double bond, where they have kind of this double dative interaction from carbon to beryllium. And so these are the types of systems that we're interested in, and the types of reaction, the oxidation and reduction chemistry. I wanted to talk a moment about how these can be used to serve other blocks of the periodic table and potentially to access other low valent species. So if you think about low valent group 2 compounds as reducing agents, of course, the most prolific in that regard would be the molecular compounds, the magnesium-1 reagents by Jones and coworkers. Those have been used to access a variety of low valent species at this point. And so one of the things we did early on was we were trying to access the carbene bismuthinidine. And we did a lot of reactions with carbenes and various bismuth 3 compounds trying to reduce them. And if we use sodium, potassium, potassium graphite, we would always get free carbene and bismuth metal, essentially. And we knew that because we essentially got a colorless solution, and no matter if we performed it at low temperature or room temperature, we tried a variety of different things. And that got us thinking about the beryllium zero compound. And what we ended up doing was combining this carbene bismuth phenyl dichloride complex with that beryllium zero complex. And it ended up being kind of a perfect scenario to isolate the compound. We knew we might have had something when we got this really dark red solution. And it just so happens to be the case that this beryllium dichloride compound precipitates out of solution, leaving this bismuthinity in solution. And we were able to get a crystal structure. We wanted to use that for a lot of different reactivity, but it turns out that this particular bismuthinity is very, very reactive. And so we weren't able to do as much of the reactivity as we wanted to, but it did highlight that these molecular bismuth zero reagents may be useful as reducing agents. This is the first time that that had been observed. And so we ended up, because we had a very reactive bismuthinity, we needed to change strategies. So that's when we went to these carbo-dicarbene systems, and we used these systems to repair both monocations and dications. And I just want to highlight the immediate difference that we saw between traditional carbene systems and these carbone systems. And that is the bond shortening that happens when you move from carbene to carbone. And for these particular compounds, even in these starting complexes, because of the substantial pi donation that happens from the carbon center to bismuth, the bond distance is already pretty short. So in the typical carbene bismuth bond, we would see a bond distance of about 2.4. And here you see a really short bond distance of 2.2 to 2.1. And we were thinking about how that happens, and we would pretty much be pretty confident that it was a result of that additional pi donation resulting in that bond shortening. These are some of the shortest carbon bismuth bonds on record thus far. And you can see here that we were able to form this dication. We were also able to start with a different starting material and form the trication as well. And so we were hoping to do a lot of reactivity with those, and that's still in progress. But these compounds are actually quite sensitive to protonation. And so we've devised another ligand system as well, which I'm not talking about in detail today, but that work is in progress. Just quickly, the other half of my group works on boron chemistry, and boron is also important for these types of redox reactions. Of course, it's been used in all different types of applications for OLEDs, OPVs. You can observe HOMO-LUMO gap control for those types of systems as well, facilitated by the empty PZ orbital at the boron center. And so one of the types of systems that we have been exploring in my group are these redox active radicals. So we have at least 2 radical papers that we're working on now. And so we were able to form this borofluorine radical last year or so. So these types of radicals are also important because they can undergo redox reactions. They can be oxidized to closed shell cations or beryllium ions. And these beryllium ions are also important in catalysis. They have been used both as intermediates, and they've been isolated and used in catalysis, for example, hydroboration reactions and so on and so forth. My group is mostly interested in these compounds for their materials applications. And so we've been able to form this borofluorinium ion via oxidation, and we've also been able to reduce them pretty recently to borofluorine monoanions. And so that just illustrates some of the diversity of these types of reaction. These low valent species can be used to react with unsaturated substrates to get to these really luminescent molecules. And so this is something that my group is studying as well as new types of materials. And we've also studied them both as ways to observe thermochromism and thermoluminescent materials. And so we've formed these beryllium ions, which are red or orange at room temperature. We can cool them down -10 to -25. You can see that these, either by pi stacking or interactions with the oxygen and the boron center, mediates this interaction, and so it goes colorless at lower temperatures. You can warm it back up, so this is completely reversible. It goes back to red. And so we modeled this system because we weren't able to crystallographically characterize this particular system, showing this oxygen boron interaction being responsible for the thermochromism. But we did model it using THF, and we think this is pretty close to the mechanisms that is happening. And so these various redox reactions, depending on the redox state, it can be useful for catalysis, can be useful for different types of materials applications as well. And with that, I'll just thank my group. I'll thank, again, the organizers for giving me the opportunity to share pretty briefly. And again, I'll be able to take any of your questions. Thank you.
Thank you very much, Robert, for this very interesting talk. You really took us on a tour of the reactivity and possible application of main group species. So I have one question from the audience, and this is about the applications of the beryllium cation complex. What reactions could this cation be used for?
So we actually haven't done much reactivity with this so far, and part of that is because of the challenge in dealing with beryllium. So many of you know that the toxicity of beryllium is a concern, which is why we've shifted focus to making the comparable magnesium complexes. So to answer your question is, we haven't done a lot of reactions with it, and we're unlikely to do it, at least in my group.
Okay. Are there any further questions from the audience? We still have a few minutes for questions for Robert. There is a question about the chemistry of magnesium. What will be your next focus for magnesium compounds?
Well, personally, I would like to see a magnesium radical. That's something that we've been pursuing.
Thank you very much. I have a question about the boron complexes. This is about the color disappearing upon THF binding to the boron complexes. Is that observed?
I'm sorry, I didn't hear. Can you repeat that? The color of...
Do you see the color disappear upon THF binding to your boron complex?
Yes, yes. So that was the model here. So we were unable to demonstrate, at least crystallographically, that this oxygen boron interaction from the periphery of the borofluorine was responsible for that disappearance of color. And so what we actually did was, instead of doing the reaction this way, we simply added THF, bind it to boron as a model for this oxygen, and we do see the disappearance. That's actually shown here. That's this particular experiment. So in the black trace, this is the cation without THF, and as soon as you add THF, you lose these features in the UV, and the solution goes completely colorless. So yes.
Thank you. I have a question about the beryllium magnesium complexes and whether they could be used for a CO2 fixation.
The what complexes? Sorry, I couldn't hear very clearly.
Beryllium magnesium.
If they could be used for CO2?
Yes.
We are trying that now. I will say that we've seen some reactivity with CO2 with these compounds, but it's very challenging. So we're going in that direction, but we are not ready to comment yet.
Our next question is about using beryllium 0 as a reducing agent for bismuth 3. that is maybe not something everyone would like to do. Is the magnesium 1 complex of Jones an alternative?
Yeah, so I would say that it probably is. At the time, we tried to, where's that slide? Yeah, so at the time, this was now on 2 or 3, actually, we were doing these reactions back in 2018. And so we know that this particular chemistry, it's necessary to have everything extremely pure. Otherwise, you don't have a chance to isolate these molecules. Some of them, the yield is already low, so you really have to have pure material. And we, at the time, couldn't make the magnesium 1 perfectly clean, but we couldn't make this beryllium 0 complex perfectly clean. And that's why we started there. But I absolutely agree that the magnesium 1 compound by Jones is probably a option as well. We should try that reaction and see if it works.
And I will ask one last question from the audience now, and if we have time at the end, we will continue with the questions because we have a lot of them. So our last question is, did you find a nucleophilicity on the boron center of NHC stabilized borafluorine anion?
Yes, we'll report that very soon.
Thank you for your answers, and thank you again for a brilliant talk.
Thank you. Thank you for having me.
And now I will introduce our next speaker. Oh, great, Rebecca is back. So Rebecca.
Hello. Sorry everyone, we just had a fire drill. Yeah, so, well, thank you very much, Robert, for a very nice talk, even though I may have missed some of it. Yeah, so moving on to the next speaker, we have Josep Cornella. I'm not sure. Yep, here we are. He obtained his bachelor and master degrees in chemistry from the University of Barcelona. Following this, he undertook his PhD at Queen Mary University in London, under the supervision of Professor Igor La Rosa. Following this, he took up 2 postdoctoral fellowships at ICIQ and at the Scripps Research Institute. And then in 2017, he joined the Department of Organometallic Chemistry at the Max Planck Institute in Mulheim. And today he will tell us about bismuth redox catalysis. Thank you very much.
Thank you very much. I hope you can hear me well, Rebecca and everyone, I guess. Yeah, cool. All right. So thank you very much for the invitation. I want to join Robert in thanking the whole European Journal of Inorganic Chemistry, Rebecca, for this special issue that you're putting together, and all the organizers for inviting us to give a talk here and present some of the chemistry that we have been doing. It's also an honor to be sandwiched between 2 super main group guys like Eva and Robert. So I feel a little bit like an intruder into this symposium, and I'll show you why in just a second. So, all right. So as I was saying, so our group is mainly focused, or the original idea when we started in 2017 is that we are organic chemists and we try to come up with the strategies to streamline organic synthesis. But we spent a long time to try to come up with, to study the fundamental reactivity behind these reactions that we try to develop that are new and are fast and to the service of organic synthesis. And our approach to this, to our contributions to the organic synthesis have is a threefold approach based on the design of reagents, the design of ligands that confer certain properties into transition metals, for example, or that enable certain reactivity of transition metals, and finally, which is going to be the topic of today, try to come up with new reactivity for rather forgotten elements of the periodic table, such as bismuth, at least from the point of view of organic synthesis. So just to briefly mention on the first two aspects, we develop a reagent, for example, this beryllium tetrafluoroborate here, or this sulfinyl trifluoride, and also on the right, on the middle part, on the ligand design, we design a Stilbene ligand, which is an olefin ligand that supports a nickel 0 and makes it air stable, and now you can purchase these as a surrogate of nickel COD, for example, and do nickel chemistry on the bench. So this has led to novel activation of amino groups, for example, in the case of the beryllium chemistry, some aryl sulfur 6 compounds that are precursors for suffix hubs, important for chemical biology and so on. And in the design, the ligand design, on how we think about trying to modulate properties of the metal center by designing ligands has led to these air stable complexes, this family of air stable complexes of nickel 0, and also a new way of making dialkyl ethers from a transition metal based complex. But as I was saying, today is about main group chemistry and bismuth, and I think Robert has done a beautiful introduction setting up the stage. So I will go very fast, and I will just mention to you how we got into this area from the point of view of catalysis and organic synthesis. And we wondered why transition metals were very good, as Robert was pointing out, at doing what they do, and it's probably because they are very, very good at revolving between different oxidation states during a catalytic cycle. So what we wondered at the onset was if we could translate these properties into beyond the D block into a main group element. And what we looked at is bismuth, which is this element that beautifully crystallizes when crystallized properly here, a very colorful element, but it has certain properties that also Robert alluded at the beginning, which is the price is much cheaper than second and third row transition metals, and that is linked to the abundancy of this element on the Earth crust, which is much more abundant than second and third row transition metals. And as also Robert, so thank you very much for that introduction, pointed out, there is certain low toxicity associated to bismuth, as exemplified by these, for example, two drugs here on the left, bismuth subsalicylate or vibrocathol, or on the right, bismuth oxychloride or oxynitrates, which are part of the pearly, what give the pearly color to makeup. But beyond that, what we were interested is what is depicted in this screen, right? So transition metals go up twofold in oxidation in the canonical. For example, if you think of palladium 2, for example, you go from palladium 0 to palladium 2, and then in a reductive event, you go back to palladium 0, right? That would be the simplest redox catalytic cycle for a transition metal. So what we wondered is if bismuth could do the same. So could we start from a given oxidation state of bismuth, go twofold in oxidation, and then back in a productive cycle while doing some organic synthetic useful transformation. But we have to do a little bit of recapitulation and look back at what is bismuth and what can we do. So bismuth in the past in organic synthesis has been really used. So it has been extensively used. But most of the chemistry that you will find is the use of bismuth 3 as in catalysis as a Lewis acid, right? It coordinates to carbonyls, dienes, or ethers. But all the transformations that in the bismuth remains in the same oxidation state. So if you want to do redox catalysis, you have to look at what are the electrons that are available here. And if you look at the group 15, which is where the bismuth is at the very, very end, so we have the nitrogen, which the lone pair, which are the electrons that you want to remove there, are in an sp3 hybridized orbital. But if you go down in the group, the atom gets bigger, the energy levels between the ligands that are attached to bismuth and the lone pair are much, much more different. Therefore, there is no hybridization anymore. And this lone pair exists in a s orbital, pure s orbital, and super contracted to the nucleus. So it's very, very hard to get rid and abstract those two electrons. So what we thought at the very beginning was, what if we go twofold down in oxidation state, and then we will get to this organobismuth 1, which the lone pair will reside in a p orbital, and probably that will be much more easy to oxidize. So this is what is about the first part, and then after that, I'll try to show you what are our efforts in another type of platform of a two-electron platform, which is how we are going to take these challenging electrons from the core, from the s orbital 6s2, and get rid of them to go to access bismuth 5. So in the first, there's been a lot of literature from the seminal work of Tokito and the Bismuth 1 complexes. There has been many people that have contributed in the low valent Bismuth 1 and Bismuth 2 complexes, but they are all dimeric species usually, because they are highly reactive and then dimerize. Until Dostal in 2010 showed that bismuthinidine, so Bismuth 1 complexes, could be isolated as monomeric species using these NCN bis-imine type of complexes. And it was postulated that this reduction here to Bismuth 1 from Bismuth 3 with selectride proceeds by the formation of a bismuth dihydride, which is super reactive and at -78 extrudes hydrogen to form the Bismuth 1. So another inspirational precedent for this was this transformation that I just showed here, where Radosevich in 2012 showed that ammonia borane could actually engage with azo compounds to reduce them under catalytic conditions of phosphorus using these Arduino ONO phosphorus 3 T-shaped complexes. And he crystallized the phosphorus dihydride and he subjected that stoichiometrically and saw that this is the catalytically active species. So by putting these two kind of concepts together, our proposal was, can we have a Bismuth 1 complex that is similar to the Dostal, and then we have a hydrogen donor that would go up and give you the bismuth dihydride, and then this hydride, before it extrudes hydrogen, if we have an acceptor, it will hydrogenate. So that was the original idea, and we could do that beautifully with just 1% more of bismuth, a little bit of water at almost room temperature, 35 degrees, and we could hydrogenate a variety of azo compounds, and also nitro compounds would stop at the hydroxylamine stage. And I don't want to get into too much detail into this, but we looked at very intensively at the mechanism of this, and we saw by mass spec this highly reactive bismuth hydrogen species could be detected by high resolution mass. I want to say that these are very, very reactive intermediates if they are formed, and therefore isolation of bismuth hydrates is very, very, or even detection by NMR is very, very, very challenging. But what precluded all the information that we could gather was actually the ammonia borane. So ammonia borane is a solid. The byproducts are really tedious to analyze because they are insoluble. There is a mixture of them. The presence of water also contributed to accelerate and decelerate the reaction. So it was a little bit of a nightmare to analyze the mechanism of these transformations if we wanted to gather even more information about it. So the problems that we had was mainly that the hydride and the proton of this reaction were residing in the same molecule. So we wanted to know the role of the proton and the role of the hydride. It was very difficult, right, separately. So the second thing that we had to fight against was this water that we always needed here, and it seems to be not impressive. Like it's not mandatory to have water there, but if you have water, then it acts also as a proton source, right? But it's not the only one. So the NH3 part of the ammonia borane is also the proton source. So what we decided at this point was, let's go back to the board and develop from scratch a new transfer hydrogenation protocol that will allow us now to have the proton and the hydride in two different molecules, like in this trifluorophenol or this HPPIN, and now we can analyze separately what is the role of the proton and what is the role of the hydride. And this reaction, we just developed new catalysts, as you can see on the right. Apart from the Dostal complex on the top, there is this imine amine in the middle, which is like an imine on one side and an amine supported arm on the other side with an NH bond. And at the bottom, there is this dimethylamino imine. And these two catalysts are really, 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 really active in this reaction, giving you quantitative yields of transfer hydrogenation in just 0.011% at extremely low temperatures. So super, 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 super active. And we are looking at the mechanism of this. It's a very complex reaction. It looks very similar, but it's very complex. And we are still working on it together with Alex Auer and Kalishanka here at the COFO from the theoretical point of view. So another reaction that we apply this type of redox chemistry is in the degradation of N2O. So we all know about this gas that is kinetically inert, so it's very, very difficult to react, but thermodynamically it's very potent, right? Because upon oxygen removal, you have N2 as the only byproduct. So with that in mind, we just took our bismuth complexes and we thought that maybe we could just generate this bismuth oxo type of intermediates here, which would be a bismuth 3. And then in the presence of a reducing agent that we had this experience with that, could go back down to bismuth 1, which is one of the challenging steps, as Robert also alluded to earlier, to go back and regenerate the low valence species by just grabbing this oxygen by the boron compound. And this actually works up to 6,700 turnover numbers, which is an impressive number, comparable or even beyond what transition metals can do. So here is structural proof of the bismuth 1. Upon exposing this bismuth 1 pincer complex to N2O, 1 atmosphere, you just get this bismuth oxo dimer here, where the bismuth has dimerized completely, and you have this diamond core in the middle. And if you take that complex isolated and you subject it to reduction conditions, you get a HOV and the formation of the bismuth 1 almost quantitatively around 80% yield or so. So the last contribution that we had into this low valent redox platform comes into the catalytic hydrodefluorination, which is basically the removal in a polyfluorinated aromatic system, the removal of one of the carbon fluorides and replace that one for a carbon hydride, for a hydrogen atom, right, to make a carbon hydrogen bond. So, and at the very beginning, when we took Dostal's complex that was reported by Dostal, this bis-imine with 2 terbutyl groups in the system, the reaction was very, very slow, if anything. And at 60 degrees in more than 20 hours, we just got less than 1% yield of the product. But then the student thought that if I change these imines, maybe I perturbate the reactivity of the lone pair, right? And that can probably trigger the carbon fluoride activation much faster. So in an attempt to make the bismuth more nucleophilic, so he changed these imines by oxazolines, like the one depicted here. And as you can see now in catalysis with just 5% more, this bismuthinidine, which is a novel complex, gives you 40%. And if you increase the electron density onto the bismuth by just placing electron donating groups at the para position, the reactivity goes up to 74%. We crystallized both bismuthinidines here, and what we saw is some sort of, we saw some correlation here on the carbon bismuth distance. So when the complex had almost no reactivity, the distance is 2.14. And as this carbon bismuth gets longer, the lone pair gets more localized. There is no donation back to this carbon here anymore. And then the reactivity increases because it's a much more reactive bismuth 1. Or at least that is what we think at this moment. So there is a little bit of a scope here. There are quite interesting compounds for you to look at that they are, I'm not going to comment on the functional group reactivity, but they have to be very activated carbon fluoride bonds that you can functionalize. So the mechanism, we spent a long time trying to figure out whether that is a redox mechanism or not, but we finally figured out some interesting points on this mechanism. We think this is the mechanism, and I want to walk you through. So we crystallized the bismuth 1, so we know that we start with that. And then when you mix this bismuth complex with an aryl fluoride, what you get is this bismuth aryl fluoride compound. But this is a mixture of, is in equilibrium with a lot of things, and we thought that this fluoride that is in theory trans to this aryl is actually the one that generates all these equilibriums. So the student that was working on this UF thought, if I remove this fluoride and I crash it out and I make this complex as a cation, maybe there is a chance to oxidize, to isolate this oxidative addition compound. So just by mixing, since the very beginning, the aryl fluoride and lithium triflate, he could isolate the oxidative addition product by just removing lithium fluoride from the system. And here we could get an X-ray of the bismuth 3 with this pentafluoropyridine in the apical position here, perpendicular to the plane. And then another interesting point in this reaction is that when you take then this carbon fluoride, this intermediate after oxidative addition, and you mix it with a silane, which is your hydride donor, what you see by NMR is this bismuth hydride, which I told you that is very, very reactive, right, in the system with the bis-imine. But now what we can get is an NMR of it, and we can actually freeze it. And we can see it at low temperature, -70, -50. And what we see, it is evolving slowly over time, forming bismuth 1 and the carbon hydrogen compound that we want, right? So this intermediate bismuth hydride just kind of reductively eliminates it, that undergoes ligand coupling to give you the carbon hydride, and the lone pair goes back to the p orbital of the bismuth 1. And how we know this is the bismuth hydride signal, it appears at 24.5, so which is a pretty high ppm situation here, and this is comparable to the only bismuth 3, so bismuth diaryl hydride that was reported by Powers in this Angevante, and it was determined later on what is the position of this hydride, and it appears at 19.4, and it comparable. The reactivity that they obtain is also the formation of bismuth 3 upon heating at much higher temperatures, because the bulkiness of these mesothions prevent further reactivity. So with that, this is how we provided some new reactivity, I would say, for the low valent bismuth catalysis platform. And with the last 7 or 8 minutes, I will try to explain you a little bit about the bismuth 3,5 redox catalysis, the much more challenging that I told you about. So what we thought was to look into this reaction. I'm just going to cut the story short, very short. So what we wanted to do is to convert aryl boronic acids into an aryl fluorides, and that was our benchmark reaction to try to design and develop a bismuth 3,5 redox cycle. And this was the naively proposed redox cycle. A bismuth 3 would transmetallate with a boronic acid, give you the aryl bismuth 3. After oxidative addition with some sort of fluorinating agent, gives you the bismuth 5 fluoride, and reductive elimination ligand coupling gives you the carbon fluoride and regenerates the bismuth 3. But at the very beginning, which is cool, is cool and it's not cool. So nothing was known. So there was not much literature that we could look at. The transmetallation of bismuth 3 was not known. The fluorination was only, the oxidative addition was only performed with fluorine as oxidant. And there was one obscure example in this ChemLab in 1999 by Kinya Akiba that suggested that this carbon fluoride bond formation is feasible. So cutting the long story short, as I was saying, this sulfoxamine, this diphenyl sulfoxamine backbone for the bismuth proved ideal for this carbon fluoride bond formation. So we prepared this bismuth trifluorosulfoxamine ligands here. We oxidized them with xenon difluoride. We obtained these trans difluoride complexes, which upon heating at 90 degrees, we got the carbon fluoride bond formation. So we got crystal structures and structural evidence for 3 intermediates that I show you here, the 3 bismuth compounds that I show you here. And with that, basically what we had, at least in mind, was solved the problem of oxidative addition and reductive elimination. So the only thing that was left was to do transmetallation, right? So transmetallation succumbed after a few weeks after developing these 2 elementary steps. And with a little bit of potassium fluoride and a boronic acid or a bipene, we could prepare a variety of these aryl bismuth 3 sulfoxamine with a CF3 attached to this nitrogen. Right, so the functional group tolerance is okay. We can prepare several representative examples of this. So in theory, all these steps are working in synchrony. So they are not working in synchrony, they all work, but we don't know if they can work together to do a full catalytic cycle, right? So it took us a little bit more time to develop the catalytic cycle, but here it is, right? So an aryl bipene with this 2,6-dichloro pyridinium fluoride as a replacement for the xenon difluoride, slightly milder fluorinating agent, catalytic bismuth, a little bit of sodium fluoride, heating 90 degrees, and this is just a representative selection of what we can do with these systems. So the catalytic cycle, as I mentioned, we try to provide evidence of every single elementary step. So from bismuth 3, we get to this triaryl bismuth 3, which upon oxidation, you get to the bismuth 5. And we have a spectroscopic and now crystallographic evidence of that intermediate, but this will come soon. And reductive elimination gives you the carbon fluoride product and regenerates the bismuth 3 tetrafluoroborate. So these are canonical organometallic steps. This is important to point out in a redox cycle performed by an element that is beyond the D block, right? So that was kind of an interesting situation. And in the last 2 minutes, I will show you another aspect of this 3,5 catalysis. And this was much more kind of fundamentally interesting. It was kind of a detour from the synthesis focus that we are here a little bit in the lab. And it's the fact that if you want to prepare a transition metal complex that has a triflate as a counter ion, you usually put that there to allow other coordinations to go in, right? So in other words, the triflate is not a coordinating anion, usually. And if it's a coordinating anion, you usually need high oxidation states to bring it into the coordination sphere in transition metal complexes. Therefore, if you want to make the carbon triplet bond via reductive elimination of a transition metal complex, that is going to be extremely challenging, if it happens at all. So there are certain complexes here that I wanted to highlight, right? So for example, this nickel 4 with a triplet in the outer sphere because you allow acetonitrile to come in, or this palladium 4 in the middle, right? So in all these complexes, any reductive elimination will happen before the carbon triplet reductive elimination, right? So that's why triplet has been so successful in these cationic or pseudocationic high valent complexes. So the question was that, and then doing literature on this bismuth chemistry, what we found is in this paper from Mukayama in heterocycles and ChemLed, we saw that this bis-diphenyl sulfone bismuth 3 complex, when oxidized with MCPBA in the presence of triplic acid, it would form 29% of this aryl triplet. And presumably that proceeds via this bis triplet bismuth 5 upon oxidation with MCPBA and then exchange with triplic acid, right? So then we thought maybe we could develop a catalytic method, which is some sort of a Nullmann or a Chandlam type of coupling in which your own nucleophile is a triplet, which is a non-coordinating, non-nucleophilic all sorts. So that actually took us a little bit of time. We changed the bismuth catalyst. It's not a sulfoximine anymore, it's a sulfone with 2 CF3s in the para position with respect to the sulfone. And with that catalyst, now one can take 1.1 equivalents of sodium triplet and 1 equivalent of aryl boronic acid and prepare a variety of aryl triplets. And the yields are pretty good across the board with good functional group tolerance. But what is more interesting is that even non-affiliates also work, and they work even better than the triplets. So the yields are quite high, and these are all isolated yields. So this is a coupling that is beyond the reactivity of a transition metal, which is quite unique. Synthetically, still maybe not perfect, but from the fundamental point of view, I think it's quite cool. So the mechanism, we think it proceeds in the same way than the fluorination, but just after the oxidation, you have a rapid exchange of fluoride by triplet because bismuth is much more oxophilic, and then by a 5-member transition state here, which is consistent with works from Liam Ball and Motherwell and Finette and Barton in the past with bismuth 5 complexes, you get the reductive elimination to form the aryl or the ligand coupling to get the aryl triplet, and you recover your propagating species. So with that, I hope I convinced you that we provided 2 different redox platforms for bismuth. And what is interesting here is that is one sole main group element and can give you 2 different types of redox cycles, right? The low valent 1,3 and the high valent 3,5. So as Robert also was pointing out, we're working with p orbit electrons and in p orbitals, and on the other hand, we are working on electrons in s orbitals. And with that, I just want to conclude saying that these this kind of a 3-fold approach has been quite successful for us, and we're keep pushing the 3 kind of directions even further, see where we're going with this. I just want to thank the people that have contributed dramatically to all this. Big shout out to Uri here, who will start soon his independent career. He has been handling all the bismuth chemistry since the very beginning. So super thanks for that, and all the rest of the group members, all the collaborators that have contributed dramatically to all this chemistry that is very, very challenging in terms of analysis and crystallography. Finally, the people that pay the bills, and I would like to thank you all for your attention, and I'll be happy to take any questions. Thanks once again for the invitation. It was really nice to be here. Thank you very much.
Thank you very much for some very beautiful redox chemistry with bismuth. So we have quite a lot of questions from the audience, so I'll just open those up. So the first one we have here, I guess, what is the role of the ligands in making and I guess stabilizing the bismuth hydride complexes?
So the bismuth in the bismuth one, the bismuth hydride, yeah. Yeah, so we have observed the bismuth hydride already more than once. So we reported it once, but in the lab we have already observed it observed it in another ligand framework. But with the bis-imine terbutyl, for example, when we try to fish it there, we can't in the same way that we have it with this bisaxazolene. So I don't know if it's only the ligand, the pincer ligand, but also the substituent that is hanging from there, like the pentafluoropyridine, for example, if it plays also a role there. This is a very new in our lab, and we are really looking into that and try to find out, because they are super reactive and very interesting compounds.
Yeah, certainly, yeah. Another question, in the, I guess, the first part of your talk, when you're looking at the azo reduction reaction, have you ever tried those reactions using neat reaction conditions? I guess without solvent.
No, I don't think so. We've done solvent screening for sure with a lot of different solvents, but never neat. Why never neat? So at the beginning, I think, so ammonia borane is solid, the azobenzene is solid, and the bismuth is also solid. So at the very beginning, there was no element there that would give us a little bit of, but now we have HBP in this new system. We could try to do it neat. I don't know. I would like to know if there is any reasoning behind the neat conditions, or if somebody could come. So the guy that, or the, sure. The person that, okay.
Yeah. And I guess with sort of relating to the reduction chemistry, can you reduce other functional groups, such as, I don't know, carbonyls or nitriles, using those systems?
We can reduce some. We tried some things. Carbonyls were difficult. It depends on the substituent that we have on the R group that is attached to the carbonyl. I think imines we could, but yeah, there were so many methods to reduce imines that we're kind of, I don't know, like, yeah, so, like we decided maybe not to pursue that. Yeah. And carbonyls, I think it might be some. Yeah, some, but it were very specific. If something, it was very, very non-general, right? Like very, very substrate specific, and we didn't even probably run the blank to see whether the reaction works without catalyst. So,
another question here: how do your bismuth catalysts compare to, I guess, the sort of equivalent transition metal complexes that you would use for these reactions?
For which reaction, right? So that's the question, because in certain instances we can do similar, in certain instances we can do slightly better. So for example, I can comment on the carbon fluoride is like extremely active. The N2O, for example, is extremely active. 6,700 turnover numbers, super impressive. And that I think, and if I remember correctly, is probably higher than the transition metal. But for example, the fluorination in the high valent, right? There was, when we reported that, there was not a single transition metal catalyst that could do the fluorination of boronic acids via organometallic steps. There was only one example by Tobias Ritter through single electron transfer processes, the outer sphere, and so on. But by just making metal, or I would say, yeah, metal carbon bonds, you did not have the complete catalytic cycle, and that was kind of very like a unique thing. And also the triplet, right? The triplet you cannot do it with a transition metal.
Yeah, and I think this is perhaps, I guess, one of the advantages. If you're looking at main group catalysis, is when you can get different or new reactivity.
Yeah, exactly.
So in the fluorination reaction, what is the rate of the background reaction where your F+ equivalent reacts directly with the ISPO substitution?
So we've done the blanks because we were very concerned also about it at the very beginning, because there were reports on direct fluorination of boronic acids with select fluor, for example, I think, if I remember correctly. But those boronic acids that they need to be electron rich, very electron rich, all of them, like with methoxys all over the place, or even naphthalene or so on. So we done, for all those reactions that I showed, we've done the blank. And if you mix the boronic acid and the base, or without the base, or with the, you know, like there is no fluorination of the boronic acid. So we were very cautious about it. And it might be that one substrate will give you 15% yield under these conditions, but certainly not the 80 or something like
Okay, I'll just ask a couple more questions. There's quite a few, so I'm sure perhaps you can answer some of these later offline. Question here, to synthesize your Bismuth 1 species, you use your bis sort of imine ligand in the first part. How are imine or oxazolene sidearms effective for the catalysis, and is it possible to change these sidearms to amines or phosphines?
Right. So in our hands, what we've experienced, bis imines, you can stabilize the bismuth 1 and isolate it. Imine amine, you can isolate it and stabilize it. 2 amines will give you immediate decomposition, and we cannot isolate them. Okay. So far, we cannot isolate them. So bisphosphines, we've never been able to isolate any of the bismuth 1s thus far. So I don't know. We haven't tried extensively to put 2 phosphines. So what they are crucial for catalysis indeed, as you have seen, for example, in the CF activation, for example, if you have the oxazolines or you have the imines, any imine, because we prepare with different substituents, not only terbutyls, they are completely different, and the oxazoline performs much better in that particular reaction under the catalysis. So yeah, it's crucial. Okay. One over the other one. Yeah. Also, the bismuth nitrogen distances are different on the bismuth bis imine and the bismuth bis oxazoline. And the oxazoline is slightly more open, and that also affects the catalysis, not only the carbon bond bismuth distance.
I'll just ask one final question. Is there any chance of doing cross-coupling reactions or CH activation using your bismuth?
Yeah, that's the golden ticket, right? Let's see. That's all. Good
luck. Good luck with that. Yeah. All right, well, we'll leave it there. Thank you very much again for an excellent presentation.
Thank you, guys.
Yep. Beautiful chemistry. Thank you.
Thank you. Thanks. All right.
Okay, so now we'll move on to our final speaker of the afternoon. So next up, we have Professor Eva Hevia from the University of Bern. So a bit about her background. She did her master's and PhD degrees in Spain at the University of Oviedo. She then went on to do postdoctoral studies at the University of Strathclyde with Professor Mulvey. Following this, she then stayed in Strathclyde, first of all on a Royal Society University Research Fellowship, and then slowly worked up the ranks to full professor in 2013. And then 2 years ago, she moved to the University of Bern. And today she's going to tell us about exploiting cooperativity in main group metal catalysis. Thank you.
Thank you very much, Rebecca. I hope you can all hear me well. Yeah. So first of all, I also would like to start by thanking the organizers and of course European Journal of Inorganic Chemistry for arranging this event, and also for letting me share the stage with 2 fantastic speakers. So it's a pleasure to be here today sharing some of my chemistry with Pep and also with Robert. Let me perhaps move you now to another part of the periodic table that where we have been just now, and I would like to share with you some highlights of our work looking at cooperative catalysis using S-block bimetallics. And of course, when it comes to polar organometallic chemistry, I think it's fair to say that in the last 10-15 years there has been a genuine revolution in this field with the realization that bimetallic compounds that combine an alkali metal with another main group metal, like for example zinc, magnesium, or aluminium, they can actually offer unique chemistry that cannot be replicated by the monometallic components. So in the best cases, you can have exceptional reactivity, very unique reduced selectivities, and functional group tolerance that are not possible with, for example, group 1 organometallics. And organic chemists have already taken advantage of these properties in many stoichiometric reactions. And for example, Paul Knochel has shown that combining a magnesium amide with lithium chloride, you can actually functionalize aromatic molecules via the protonated metallation, even when you have very sensitive functional groups. And here you have another example from the group of Ukiyama in Japan, where he promotes activation of this carbon-bromine bond using this lithium zincate, which is compatible with quite reactive functionality like an alcohol. And actually, some of this chemistry has been beautifully summarized recently by Rob Mulvey in a chemical reviews. And in this article, actually, he has this very, I think, thought-provoking talk that basically tries to emphasize how the chemistry of these metal pairs is so unique, is so synergistic, that actually you can create a new periodic table just made up of different metal pairs. So today I want to focus on just one type of bimetallic systems, because in our group we are fascinated with this type of bimetallic compounds, and we have worked with many different combinations. But today, for the sake of brevity and to keep myself to time, I'm going to talk about some highlights of our work looking at the chemistry of alkaline metal magnesiates, and actually how we can use these systems not only stoichiometrically, but how we can upgrade these cooperative effects into main group catalysis. But before I show you our catalytic studies, I want to show you a very recent example of cooperative chemistry for our group in a stoichiometric reaction, looking at magnesium halogen exchange reactions. And why I want to show you this is because hopefully with this study I can emphasize how fascinating the chemistry of this bimetallic systems is, how important is the cooperation between the two metals, and also how complex the solution chemistry of these reagents sometimes can be. So if we think about metal halogen exchange, of course, this is one of the most powerful methodologies we have in our hands to functionalize haloaromatic systems. And these are reactions that we carry out usually in the lab using an organolithium reagent. And they are kinetic processes that are driven by the stabilization of the carbon ion that is generated. And of course, the strength of this bond, the carbon-halogen bond, depends whether you have an iodine or a bromine or a chlorine. These reactions have been around for quite a long time. Of course, Gilman and Wittek pioneered them a long time ago, and they are kinetic processes. So because they happen very fast, actually we can use very low temperatures. We can go down to -78 Celsius without having a problem with the lack of reactivity and trying to control the selectivity or functional group tolerance of the organolithium compound. But when it comes to magnesium, the things change quite a lot, because magnesium doesn't have the kick, it's not reactive enough on its own to promote metal halogen exchange of bromoarenes, at least not dialkyl magnesium compounds like diacetyl magnesium. But what we found in collaboration with a group of Paul Knochel in Germany was that if we add to the mixture one equivalent of a lithium alkoxide, this lithium alkoxide that you have here in the slide has a long aliphatic chain, you go from nothing to almost everything. So in just 30 minutes, you get quantitative conversion, and of course, of the exchange reaction. And of course, the group of Paul, who are fantastic synthetic chemists, can then do a very beautiful organic chemistry and further functionalization of these aromatic scaffolds. But for us, when we entered this project, the big question was like, how is this possible? What is the effect, or what is the role that this lithium alkoxide is playing in the reaction? So for that, we tried to look at this part of the reaction, and we tried to isolate the intermediates of the exchange. And when we did that, the first thing that we found out is that we form a bimetallic compound. We actually form a lithium magnesiate. And I always tell my students that every structure tells you a story, and definitely this structure here is telling you a very interesting one, because you can see that the magnesium atom is occupying the position that before was filled by a bromine atom. So basically what we have here is a genuine magnesium bromine exchange. But also look at the coordination of lithium, because lithium interacts with the alkoxide group, but also is stabilized by these interactions, lithium oxygen interactions from the substituent of the arene, from the methoxy group. And actually, once we know that these structures are favored and stabilized by the formation of these interactions with alkaline metal, then we can tune the reactivity of the systems. And we can look at molecules like this one here in the slide that has a bromine and an iodine. And of course, I mentioned before, iodine carbon bonds are much more reactive than carbon bromine bonds. And here, we swap this order of reactivity by the cooperation between the two metals, by the coordination of the lithium that gets stabilization through these methoxy groups. We selectively cleave the carbon-bromine bond and we let the carbon-iodine bond intact. And another synthetic application of this cooperation is the fact that if we have a polyhalogen substituted systems like this dibromopyridine, we can selectively functionalize with this combination of the diacetyl magnesium and lithium hydroxide the bromine that is next to the nitrogen of the pyridine, because that favors again the formation of this compound. So yes, magnesium is stabilized because it's part of an A and enhances the kinetic reactivity of the magnesium carbon bonds. But also, as you can see here, lithium is a major player. Both metals are important because lithium is kind of controlling the regioselectivity of the reaction. And of course, or I hope many of you looking at these structures may be wondering, well, what happens if you send the substituents far away? What happens if you have a methoxy group, say, for example, at the para position? And that was exactly what we did in the lab. Yeah, we wondered what it would be. And we were up for a surprise, because when we do this reaction, actually what we see is the formation of magnesium alkoxide. I think I must say that all these reactions, I show you the structures that are very eye-catching, but we also monitor them by NMR, and we can see that this is exactly the same that we have in solution. So we see the formation of magnesium alkoxide, and also we get a new type of bimetallic compound, a compound that only has aryl ligands. And if you look at the ratio of lithium to magnesium, we have now 2 lithiums per 1 magnesium. And this was quite of a mystery, how we could have this compound starting from this combination, and how apparently the substitution of the suster was really dictating the constitution of the product. So what we did, what my students did, was look back at the constitution of the exchange reagent without the suster. What was happening when we combine diacetyl magnesium with lithium alkoxide? And again, with the help of NMR, we can see that initially we form this mixed alkyl alkoxide system. So the two reagents, they come together and they co-complex. But this compound in solution actually is in equilibrium with this tetra-alkyl lithium magnesite and this magnesium alkoxide. And when you look at this, it may look complicated, but actually what we have here is just a new version or a different version of the classical Schlenk equilibrium, but in this case for bimetallic systems. So we have this heterolectic lithium magnesite that is in equilibrium with this homolectic all alkyl tetra-alkyl species and the magnesium alkoxide. And that really suddenly point out that there is another species that could be responsible for these exchanges, and not as we initially thought. So in order to understand a bit better how this compound behaves, we prepare it purely by mixing s-butyl lithium and diacetyl magnesium. And what we found is that this compound can also react with the 2-bromoanisole that I showed you at the beginning. And it forms this tetraaryl compound, which is perfectly stable in solution. Yeah. But if you take these isolated crystals and you dissolve them in toluene and add an equivalent of magnesium alkoxide, actually you get the co-complexation of the two systems together to form this product that is exactly the same one that we have when we get the 1-to-1 mixture of diacetyl magnesium and lithium alkoxide. And even getting a bit more information in this complicated jigsaw is the fact that if we prepare pure the compound that only has alkyl and alkoxide groups, this dialkyl alkoxide lithium magnesite, the exchange reaction does not work. So really what it shows you here is in these reactions, actually the active species, the active reagent that is promoting the exchange reaction is this tetraalkyl lithium magnesite. And why I introduced this compound here is because very related species to that are the ones that I'm going to show you in 2 minutes in terms of catalysis. Yeah. So just to put all this together, I'll try to summarize this part of my talk. When you combine the lithium alkoxide and the dialkyl magnesium, initially what we have is a co-complexation to form this mixed ligand species, but actually this compound is in equilibrium with the tetraalkyl lithium magnesite and the magnesium alkoxide. And this compound is significantly more reactive. And I guess that is not surprising if you think about it. Formally, magnesium here is coordinated to 4 alkyl groups. So formally, you have a dianionic magnesite, whereas here your magnesium is monoanionic. So this will be the species that will react with your bromoating, whether you have substitution in ortho or in para or in meta. And you will form a tetraeder lithium magnesium, but of course, along with the magnesium, you have the magnesium alkoxide. And now you have two different fates. If the functional group is remote to the alkali metal, so it's remote to the ortho position, the compound is stable, and this is the one that you quench with an electrophile and gives you organic product. But if it's close to the ortho position, then you can favor this type of interaction, this kind of co-complexation to form the mixed alkyl alkoxide species. That once again, once you treat it with an electrophile, it will give you the same. And the reason why I'm showing you this part of the equation is because sometimes when we do organic chemistry, and I like organic chemistry a lot, we kind of don't get to see, if we just look at the final product, we cannot miss all this fascinating chemistry that is happening in solution. And it's also helping us to understand how the systems operate, which is the real active species in these exchange reactions, and how lithium and magnesium can help each other to promote this reactivity. So with this in mind, the next, and with this finding that these tetraalkyl lithium magnesium are so reactive, we wonder for a while in the group whether it's possible to upgrade or to transfer this cooperative chemistry into catalysis. And when it comes to catalysis, of course, organolithium reagents, linear reagents are not that popular. I guess that we all agree on that. They have many applications in stoichiometric chemistry, but when it comes to catalytic applications, well, they are not so selective sometimes. They have limited functional tolerance, and as we have seen, it's already been mentioned by Pep and Robert, they have limited redox activity. Yeah, but in reality is that H-block metals are actually fantastic catalysts, and there has been seminal contributions from people all over the world, like Michael in UK, Short Harder in Germany, or Carpentier in France, that have shown that group 2 amides, in particular those from the heavier elements like calcium, barium, strontium, they are fantastic catalysts when it comes to hydroelementation reactions. They have found many applications in hydroboration, hydrophosphonation, hydroamination, and so on. What is fair to say as well is that in many of these processes, magnesium seems to be the less reactive of the group. And this, of course, has been attributed to its size and also to its different electronegativity, because in these catalytic cycles where the metal does not change the oxidation state, what is proposed is that first the calcium or the barium precursor reacts with the amine to form a highly nucleophilic calcium amide, but in turn that can then insert the organic molecule, as for example styrene, through an intermediate of this type or a transition state of this type, where calcium can also polarize and activate the carbon-carbon double bond. And this is the step that is the rate determinant step of the catalytic cycle, but also is the part where magnesium cannot do as well as these other larger metals. Then the intermediate of insertion can be easily protonated by the excess of amine, and that is how you liberate your final product and regenerate the catalyst of the reaction. So since magnesium on its own cannot do it, we wonder if perhaps with a little help of sodium, lithium, potassium, we can make it work as well as the other metals. And the systems that we prepare and the precursors for the catalytic reactions that I'm going to show you for the rest of my talk, they're actually quite simple. They're made up by the co-complexation of the group 1 alkyl and the magnesium alkyl in a 2-to-1 ratio, and using a nitrogen donor like TMDA or PND that can help you to grow crystals of these compounds. And the alkyl group that we use is this monocellular group that you have here. And the reason for that is because the precursor is commercially available. That for us is always very important. Also allows for the crystallization of these compounds, so you can have them as solids that you can weight very accurately. And also it doesn't have hydrogens in beta, so that allows you to heat if you need to heat without having to worry about the decomposition of the alkyl groups. So when you do this reaction, these components, they self-assemble nicely to form this magnesium compound. This is the structure. You can see that magnesium is attached to 1, 2, 3, and 4 alkyl groups, and its sodium interacts with 2 alkyl groups and is solvated by the donor, like TMDA. And with potassium, you get exactly the same type of motif, but in this case, the donor that we use is a tridentate ligand, is PN beta, because of course potassium is larger. And the idea behind this type of chemistry, or looking at these compounds as pre-catalysts, is because we thought, or we envisaged this project in terms of having a double activation in our catalyst. In one way, we are enhancing the nucleophilic power, the basicity of the magnesium by the formation of this magnesium scaffold. Also, as I showed you before, the alkali metal is not sitting in the back seat, it's actually an active player, and it can be acting as a built-in Lewis acid that can activate unsaturated organic molecules. So that was at least our starting point in this project. And the first type of reactions that we looked were intramolecular hydroamination processes that have been widely explored and studied with calcium and other group 2 metals. And we found that, as our predecessors, magnesium is really not the way to go. That you can wait for a whole day and you get 0% conversion. We then look at the sodium magnesite I showed you before, and there was some hope in there. After 5 hours, we see some conversion. So definitely there's an activation, although the selectivity is not the best. But then when we swap to potassium, actually within 3 hours we get full conversion, and you can see that we have a much better control of the selectivity. And for us, this was very exciting, and it was big news because actually it showed us that the alkali metal was actually be able to play a role in this catalysis. And we can extend these transformations also to styrene, and trying to understand the intermediates that are involved. If we react the alkyl compound with an excess of amine, we can isolate and crystallize these tetraamido systems that are highly nucleophilic, and they retain this structure in solution. So this was our first catalytic study, and here what we can propose is first you form this tetraamido potassium magnesite, to which the styrene, in this case diphenylacetylene, can coordinate to the alkali metal through the formation of pi interactions that of course are very well known in potassium coordination chemistry. And this will bring the alkyne very close to the nucleophilic amide and facilitate then the insertion reaction. And of course, once the intermediate is formed, then protonolysis with more amine will generate the final product. And so this was our first example where we actually could see that this idea of the 2 metals working together and helping each other to help us to activate magnesium towards this type of hydroamination processes that we can then extend also to other unsaturated systems like isocyanides or carbodiamides, to name just a few. So since then, what we have been trying to see is what is the scope of this bimetallic system and what type of reactions can we catalyze. And another type of reactions that we were quite interested in was the cyclization of alkenols. And these reactions, they can be catalyzed by transition metals, but when it comes to S-block metals, they are quite demanding in terms of time, and also sometimes the conversions are not very good. So there is a study from Hell where he needs to keep for 16 hours with this strontium amide, and the yields are not, or the sensitivity scope is quite limited. So what we found here is that neither magnesium, neither potassium is the way to go. We can hit for a day and a half. So obviously the student here had quite a lot of patience, and we still have seen no reactivity at all. And when we took the potassium magnesite, yes, we see some reactivity. After a day, we get 91% conversion, but of course it wasn't something that we were jumping about it. But why I want to show you this example is because here what we find out is that by tuning the coordination of potassium, we can actually make this reaction work much better. Because when you add one equivalent of 18 crown 6, this macrocyclic ligand that can coordinate the potassium, actually the yield goes to 94% in just 3 hours. And you can see that we can get a better control of the exo and endo product as well. So that was quite interesting. And we could actually, because the conditions are much milder, we can actually extend this approach to several alkenols, and the conversions are all from good to very good. But how does it work? Because of course we are inorganic chemists and we are very interested to find out about the mechanisms. So I'm going to save you a lot of animal studies here and kinetic studies, but what we have found is actually when we mix the alkenol, the magnesite, and the crown ether, what we actually form first is another, like the one here in the slide. And it's important to know that despite the fact that these macrocyclic ligands are selected to the alkali metal, and this is the one that is selected to potassium, because potassium is very large, there is a still coordination ability or a coordination site available for potassium to form a contact with ion pair species, because it's very important to know that in all this chemistry, we need potassium and magnesium, or the alkaline metal and magnesium being very close to each other to be able to communicate. Kinetics show us that the formation of this adduct, where an extra equivalent of suster coordinates to magnesium, deactivates the catalytic process, but the crown effect actually favors the disequilibrium and the decoordination of the substrate. And then, of course, now we can see how the potassium can interact with the triple bond and facilitate the insertion process. But of course, then can be easily quenched by the excess of the alkene to reform the active species and form the final product. This, of course, this catalytic cycle A will explain how we get the exo product, but I show you that there is a tiny bit as well of the endo one. And also by using NMR, we can see where that compound is coming from, because we can actually see that this species in here in solution is in equilibrium with this isomer with the allyl form of it, which of course potassium can also bind to it and can also undergo insertion to form this intermediate. Well, now we have this allyl intermediate, and when it's quenched with the alkenol, it can give a mixture of the exo and the endo product. Of course, it's important to know that because we get very little amounts of this product, the prominent or the most likely, or the one that cycle that is taking place here is the one that we label as A in the slide. And very recently within the lab, we have also looked at hydrophosphorylation reactions of styrene. And why I want to show you this reaction in particular is because in this case, we have managed to isolate the intermediate with the crown ether. And just to show you that when we react the tetra-alkyl potassium magnesite with an excess of this phosphine oxide, we can get this beautiful structure where now magnesium is attached to 4 deep protonated phosphine oxide. But you can see the potassiums are solvated by the crown ether, but they're still interacting with aromatic rings of the phosphine. This is structure that you can see is much more beautiful probably than the Kendo. And actually this system we found that is also very efficient in promoting a carbon phosphorus bond formation under relatively mild conditions as well. Okay, so the last example I want to show you is how we can use these systems not only for hydroelementation reactions, but also to do ligation between acids and alkynes. And of course, when it comes to 1, 2, 3 triazoles, we all know they are privileged scaffolds in organic synthesis that present in many molecules that have biological activity. And if I ask you what's the most versatile method that you have to prepare 1, 2, 3 triazoles, I'm sure that most of you would say copper catalyzed acyl alkyne cycle additions. And that is true. This is the typical example of click chemistry. And this allows you to prepare 1,4 disubstituted triazoles. But when it comes to these other ones, to the 1,5 disubstituted isomers, there is not a method that is so versatile or so standard as the click chemistry. There is examples where ruthenium can act as a catalyst, but there are sometimes forcing reaction conditions and limitation with the functional tolerance. There is an example where lanthanide amides have catalyzed this reaction, or inorganic salts, but again, there is always a problem with the substrate scope and also with the harsh reaction conditions. And in terms of S-block metals, yes, they can catalyze, they can promote this reaction, but only stoichiometrically. There are no examples of catalysis to promote the formation of triazoles. And unsurprisingly, when we try the addition, or we try the reaction of phenylacetylene with benzyl ethide, lithium alkyl, sodium alkyl, you get very low conversions. Potassium trioxide, maybe a bit milder base, you get no reaction at all. The potassium, we then tried the magnesium alkyl, and that was a good result, because within 6 hours we can see 100% conversion. So that was quite good. And then we tried the potassium magnesite, thinking that it was going to be even faster and better. And actually, we were up for disappointment, because after 1 hour, after 1 day, we got 64% conversion. So in this case, the potassium magnesium combination was not the best. But, and this is where the doubt comes, the potassium magnesium was not a good marriage, but the sodium magnesium was. And actually, when we use the sodium magnesite, with only 45 minutes, we get full conversion. And here, the addition of a crown ether has a very different effect, because sodium is smaller. So the crown ether, what it does is takes the sodium totally away from the magnesium. And once you break that communication, once sodium and magnesium are far away, you get 0% conversion. That shows you how important it is that the two metals are together. And this is just a slide to show you that this is a very versatile method that we can apply to a wide range of acids and a wide range of alkynes that can be aliphatic, and they can be also aromatic, of course, with different substituents. But perhaps one of the reactions that I like the most about using this catalysis is the control that we have of the reactivity, especially when we look at this alkyne species, because if we use one equivalent of the acid, we get selectively the monotriazole species. If we use two equivalents of the acid, actually we get the symmetrical ditriazole. And even nicer, if you have this mixture and you add a different acid, you can synthesize in one pot this non-symmetrical ditriazole, which shows you how controlled this reactivity is. And just to finish, we have also done mechanistic studies, and this is one of the nicest structures I think I have shown you today. The reaction of the magnesium with an excess of the alkyne gives you this tetraalkynyl species where you can see magnesium interacts to the carbon that has been deprotonated, whereas sodium is very happy forming these pi interactions with the carbon-carbon triple bond. And this compound is perfectly catalytically competent and gives similar conversions to the ones that when we use the tetraalkyl system. But also, if we use alkynes that are internal, the reaction does not work. So it really shows that the deprotonation of the alkyne is key for the reaction to work. So we can propose now this catalytic cycle, where again we start with this tetraalkynyl species to which the acid can coordinate to the sodium. And this is why it's very important to have them together and close. And this is why if you have the crown ether, you block the coordination site on the sodium and you stop the cyclization process. Then that allows for the insertion, that is the rate determinant step, followed by the cyclization and finally protonation to liberate the trans. So that is again another of these examples where we have this bifunctional system of the Lewis acid and the Lewis base together. And that really takes me towards the end of my talk. I'm sorry, I don't know if I rushed a bit, but I wanted to show you some snapshots of our work. Basically, I hope the take-home message from this talk is that when we combine two different main group metals together, we can actually get very unique reactivity that we can apply to catalytic behaviors. And of course, cooperative catalysis in transition metal is a well-established field, but main group cooperative catalysis is just emerging. And I think we have only started to scratch the surface of what this type of chemistry can really offer in catalysis, because you can imagine this is just alkaline metals and magnesium, but you can imagine all the combinations that we can explore with aluminium, with zinc, and so on. Okay, and that takes me to my last slide, but always the most important one. I want to thank first and foremost my research group. The people who are working catalysis within the group are the ones that are involved there, and they are the ones that contributed to most of the work I have shown today. Also my collaborators, all these institutions for funding, in particular the SNF, and all of you for your kind attention. Thank you very much.
Thank you very much. Very beautiful chemistry there using cooperative S-block catalysis. So we've got quite a few questions. Let's go to start. Here we are. Okay, in your lithium alkoxide butyl magnesium complexes, does your magnesium alkoxide do anything, or do you always get the same reactivity as if you take butyl lithium and your dibutyl magnesium?
Yeah, that's a very good question. So actually the magnesium alkoxide, we do not see it involved, at least in the reactivity. It's either co-complex or free, but it's a bystander. It's really, of course, we didn't know at the beginning that was the case, yeah? But now we know through these studies that it's actually, you form your tetra alkyl lithium magnesium, and that's the one that takes the role in terms of the chains. At the end, the magnesium alkoxide can come and incorporate into the structure of your metallated intermediate, but at that stage, the metallation has occurred.
Okay, thank you. Another question, I wonder whether the lithium magnesium cooperativity is actually our alkoxide magnesium cooperativity, especially considering the Schlenk equilibrium that you presented. Did you ever try to replace your lithium alkoxide to I guess, the magnesium equivalent in the bromine magnesium exchange reactions.
Okay, so yeah, I think I got you. No, we haven't. But I guess, I mean, the Schlenk equilibrium is the one that we are already familiar because we all use linear reagents. But I think when you have a group 2 compound that has 2 different ligands, you always expose, or you always have the possibility of rearrangement to give you the two homoelectric species. And this is, I guess, why most of the work with calcium, for example, needs, or a lot of the work needs very stabilizing and bulky ligands to avoid this Schlenk equilibrium. So we haven't done it, but my idea is that depending on the ligands that you have, you may be having ligand scamper. Yeah. But we have in the group prepared sometimes some alkyl magnesium alkoxides, and they are stable, but they are special alkoxides that they have chelating groups. They have the amido groups pending that I can coordinate, and then they are much more strongly bound to the magnesium.
Have you ever investigated a replacement of your lithium alkoxide with, for example, potassium terbutoxide or magnesium? As you mentioned that potassium is playing an important role.
I think one of my students just now probably is laughing. Yeah, we have, and they are working on the paper. So it's very nice to see. Once, well, of course, once you have you understand a bit the work, then you can start to change things systematically. So yes, we have changed lithium by sodium by potassium, and we do see a trend, and we see that actually potassium induces makes the system much more reactive. This is something that we are hopefully preparing for publication very soon.
Okay, and I guess yeah, I guess it's related to this question. And the important role of potassium in potassium magnesium catalysis can probably only be fully evaluated when you completely get rid of it. So did you ever try to encapsulate it using cryptand or replace it by an ammonium cation?
That's a very good question. So we have, yeah, we have, and we do see when we use cryptand, everything becomes crazy in terms that we don't have selectivity and we don't have good reproducibility. And we think that is because of that, because the potassium is no longer available, it's sequestered, so therefore you lose a lot of the reactivity. You see some reactivity, but you don't see the same. No? It's not as good at all.
Okay, and I've got one more question here. Well, there are more, but I'll just do one more. This is quite a long, complicated one. Very beautiful structures and isolated compounds. After the formation of your Li2 R4Mg species, you could use this species as a carbon nucleophile. Did all 4 equivalents of the R group work as a nucleophile? This is the first part of the question.
Yeah, this is for the catalysis. Yeah. So through the kinetic studies, what we can see is that all the R groups react with the alkyne or with the alkoxide, with the alcohol. So they all undergo protonation and they become DNS. But when it comes to the insertion with unsaturated organic molecule, whether it's the carbon-carbon triple bond or whether it's the reaction with the site, then what kinetics tells us, at least that's what we can see, is that there's only one arm out of the 3 at a time gets involved.
Okay. And I think it's part of the same question, but I think it's actually slightly different. For the cyclization of the alkynyl, conversion of your magnesium oxygen bond to your magnesium carbon bond seems to be very endothermic. Why does the reaction take place, and have you ever calculated an energy profile for the reaction?
Yeah, so this is, no, we haven't calculated it yet, but this is where I think especially that's why potassium becomes so important, because I mean, this is the one that I think in the slide I show you, without the potassium you can hit for a whole day and a half and you get 0% conversion. Yeah, you need to activate that carbon-carbon triple bond in a way that magnesium cannot do. And even when Michael uses strontium, he has to use very potent reaction conditions. So it's through the cooperation of the 2 metals and through the pi interaction of the potassium with the carbon-carbon triple bond that you can then facilitate the intramolecular effect.
Okay, thank you very much. I think we'll leave the questions there. And so thank you again. And also thank you to all of the speakers this afternoon. I think we've seen some excellent main group chemistry from both the S and the P block, covering cooperativity and also redox catalysis using the main group elements. And as Eva just said, I think we are really only just scratching the surface of main group chemistry, and I think there's a lot of exciting research that we will see in the future. Thank you.
Thank you, Rebecca. Thank you, Robert, Pep, Eva, for sharing those brilliant scientific results with us today. And I would also like to thank our audience for joining us. And if you're interested in learning more about main group chemistry and catalysis, please don't forget to visit our special collection hosted at the European Journal of Inorganic Chemistry. See you at the next Chemistry Europe Virtual Symposium. Goodbye.